Good morning, everyone. My name is Mocheshin from Western New England University. I will be presenting today the stress-induced failures of pre-stressed concrete cross ties of the railroad track structure. I would like to acknowledge my colleague, Dr. Cheng Lee, co-PI of this project, and also all the students who are involved in this project. So this is the outline of today's talk. I will be starting with the motivation and backgrounds and try to share some of the current practices of the industry and also some of the problems we have. And then I will be moving on to the numerical analysis framework I will be using based on the parallel computing algorithm. And then I will share some of the experimental testing result. And then I will be finishing up with the future work and timeline. So railroad track structure, traditionally we've been using wooden cross ties in the North America, but in many other countries, they've been moving into the concrete cross ties because it has a longer service life, less maintenance issues and cost, and the better durability. But after we move on to the pre-stressed concrete cross ties, we installed these cross ties many places, but the percentage of the concrete cross tie is still less than, well, about 5% of the entire tie, so very small amount. But in the middle 2000, we have these two derailment accidents. They are associated with this premature failure of the concrete cross ties. So FRA have investigated what is happening to this structural components. So these are the examples of the damages we've been seeing in the field. So rare seat deterioration, that's the abrasion where some damage is on the bottom of the rail, but top of the concrete cross ties where the rail sits on. And the other one is horizontal crack along the pre-stressing wires, which is one of the main focus of this study. ASR, many people already know what it is, and also center binding structural problem. So what is practiced now? So in the United States or North America, pre-stressed concrete cross tie manufacturers, they have so many different designs and also so many different wires they've been using. So depending on the company, or so depending on what wires and geometries they've been using, the performance of the cross tie is so much different. So one cross tie performs better than the other. So our so current practice is relying on our experiences. So we would like to know what is happening, what caused this problem. So one of the things I just plotted it in here on this slide is the ASTM standard for the prestressing tendons for the concrete prestressed concrete cross ties. So depths and pitch and length has been identified, how much it has to be, but the side wall angle, such angle has not been defined well. So then there are so many variabilities. So this failure type is focusing on bond slip mechanisms. So traditionally, bond slip mechanism can be explained by three mechanisms. The first one is adhesion between the concrete and the steel. The one is frictional force between these two components. And third one is mechanical interlocking due to the indentations. Also, there is a so-called Hoyer's effect. When pre-stressed wire is released, it goes back to the original position, but at the same time, due to the Poisson's effect, it tries to push out the surrounding concrete, which increase the hoop stress, so the concrete can be cracked during the releasing process. So I will be trying to tackle, or I've been studying this bond slip mechanisms. So over the years with the FLA and the Volpe Center, we developed this cohesive element which can mimic the bond slip behaviors. So we use the cohesive element with the user-defined material constitutive model. So we can mimic some of the different bond slip patterns due to the different indentations, but it has downside. So this model is phenomenological approach. So it is definitely depending on the wires and also testing. So in order to use this model, I have to calibrate the material parameters every single time, but not only one, there are multiple parameters. I don't want to discuss how many parameters are involved in this model, but it's quite challenging to calibrate all the parameters. So it is a little sensitive or highly sensitive to test results when anytime I change the concrete or the shape of the wires, I have to go through this calibration process. So I want to overcome these limitations. So what I try to do is try to model all the indentation details in full 3D. So we prepare the 3 wires. WA is a smooth wire. WG is the chevron pattern with the shallow indentation. WP is the chevron pattern, same pattern, but the deeper indentations. So on the bottom of the table, you can see that the geometrical parameters of the each indentation, WG and WP. So in order to run this full 3D model with the details of the prestressing wire, downside is the computational cost is too high. So you can see that one of the example we ran. So this is a 3 inches long one wire prism, concrete prism. So the degree of the freedom of this model is 80 millions. And again, this is too many of the degree of freedom. So I compared this simulation with the commercial software. One of them is Abaqus. And then we developed in-house code. I worked with the Dr. Kwok at the Argonne lab to develop this in-house code for the parallel computing algorithm. So for this in-house code, we are able to use 1,000 cores with 1,000 partitions. And then you can see the clear differences between these two analysis. The results are same, but one took 2 days and 4 hours with the 6 minutes. Another one with the in-house code, it took about the 52 seconds. You can see that the in-house code we developed is reliable, producing very stable and accurate result. So again, we compare these strains as well as strain distribution. So we are satisfied with the our in-house code. And also we ran the speed up test. This is a typical test that the many people will go through when they are using the using high-performance computer for the parallel computing algorithm. So you can see that we changed the number of the cores from 2 to 1,000. So you can see the analysis time can be reduced significantly when we increase the number of the cores or CPUs. But one more thing that I wanted to point out about this in-house code we developed is that the this in-house code is able to change the number of cores with a fixed number of the partitions. What that means is the many other softwares, when you would like to use 1,000 cores, you have to partition 1,000 times, or you have to have the 1,000 partitions. So partition numbers and the number of cores has to be synchronized. But this in-house code Dr. Kwok developed is capable of take different number of cores with a fixed number of the partitions. So up to 1,000 we tested it. It is run smooth and reliable and accurate. So after this, we are satisfied, and then we now move on to the full scale model. So which is 8 feet long, 8 feet and 6 inches long, pre-stressed concrete cross ties. The pattern of the wires are all different. The geometries will be a little different. So now we are ready to perform the parametric study. So now, research assistant Abdullah will be talking about some of the analysis result. Abdullah?
Hi everyone, Abdullah here. So recently, with the help of our in-house code, we performed a study on the high-performance computer to identify the role that indentation size, and shape on pre-stressing wires play in the mechanical interlocking. For that, we made 3 different full-scale models of concrete cross ties, which are embedded by different wire types, the WA wire, the WG wire, and the WP wire. With these models, using our in-house code, we performed pre-stress simulations on the high-performance computer. After the simulation, I overlapped the resulting deformed models and could identify the location of maximum displacement on all 3 models. What we realized is that the WA wire denoted by the WA wire denoted by the blue on the bottom left, on the bottom right image, the WA wire denoted by the blue color experienced the highest displacement after pre-stress release, followed by the WG and then the WP wire, which has the deepest indentation. So moving on to the next slide, we can see a graph with the 3 models that we modeled, and then we clearly see that the model that has the WA embedded in it had the highest displacement, followed by the WG, which had a 2% less displacement than that of the WA, and the WP, which had a 4% less displacement due to the indentation size of each one of the wires. So by performing this study using our in-house code, we could prove the interlocking effect caused by the indentation shape, size, and sidewall angle.
So along with the numerical analysis we've been trying to develop some engineered cementitious material shooting for the 10,000 psi strength, compressive strength concrete, but which can increase the bond or try to develop durable bond mechanisms. So we were able to develop up to 7,000 psi concrete with the aggregates locally available. We've been working with the local suppliers. They are supplying the aggregate to our research. And then we conducted a plow test to see the bond slim mechanism with the 3 different wires, WG and WP and WA. So we are able to see that clear differences experimentally. For the future work, we will be conducting parametric study with the full-scale pre-stressed concrete models using high-performance computer, and then with the different geometries and with the more wires. And then we'll be finishing up the developing durable concrete for the better bonding. So most of the undergraduate students, they are involved in this project. They are working for the durable concrete development. So I would like to acknowledge full support from the TIDC for this research. Also, I would like to acknowledge Dr. Hailey New, who is technical champion of this project, and also Dr. Park from the Argon Lab, and also North Track, which is the one of the Thai manufacturer who supplied some of the wires, and also the exit program, which I'm able to use some of this computer available at the University of Texas, Austin. Again, thank you so much for your time and attention, and I would like to welcome any questions if you have it. Thank you.